Hello, my name is Nicholas Jason.
I'm Matthew Mancuso.
And I'm Ryan Cribben, and we observed a manufacturing company who asked to remain anonymous that formed sheet metal with metal-forming brakes to meet the demands of their customers. The two systems we studied were very similar because they both produced the same products, but their differences were noted when observing the setup processes and the machine layout. Because the process produced the same items, it was very easy to quantitatively determine what system was best.
In the beginning of the video, you can see the operator setting up the automatic brake. This is the brake where the tooling is built in. He simply calls up the program, and the robotic arm inside gathers all the tooling up, sets it up for him. This tooling is completely sealed within the machine, and in order to take it out, you have to call the brake. The setup takes about 1 minute and 32 seconds. Once it's set up, the operator forms the first part, takes the part off, uses the automatic electronic protractor that's connected to the computer of the brake. The readings from that protractor are wirelessly sent, and the machine automatically makes the adjustments necessary to reach the drawing requirements for the angles. As you can see, the bottom dies remain stationary while the top dies come down, making it much easier on the operator. There's no lifting of the parts involved. Now on to the second system. This is a much older braking type. Doesn't have an automatic setup. You can see the operator having to walk across the room to gather his tooling, because now he has to manually add it to the machine. Setup on system 2 takes 3 minutes and 48 seconds. Once the machine's set up, the operator forms the first part, manually checks it, then makes the adjustments in the computer, forms the second part, and hopefully it's within tolerance.
In order to accurately observe the impact of our changes to the setup on worker flow, we created a model of the current setup of the floor. Both entry flow and the material rack must remain fixed as incoming material comes from the same area. During each process, a worker at the automatic brake or System 1 must go to the material rack and scrap bin, while a worker at the manual brake or System 2 must go to the material rack, die rack, and scrap bin. The paths of each worker were also modeled to help us identify problem areas in the system. Our first proposed change requires one additional die rack and involves putting the scrap bin where the old die rack was and placing one rack next to the computer rack for use by brake 1 and another rack between brakes 2 and 3 for use by both of these brakes. This change is both economical and has a sizable impact on the worker flow. Our second proposal requires the purchase of another automatic brake, replacing the position of brake 3 in our first proposed change. This will provide a significant increase in production with a similar level of flow as seen in Proposal 1. As the diagrams show, the intersection of worker paths along with the distance each worker must travel can be significantly impacted by a simple reorganization of the workspace. The purchase of an additional automatic brake isn't necessary, but will lead to a heavy increase in production levels.